All right, welcome to the second half of lesson 7.2. The first half we talked a little bit more about inverses, but now we're just going to talk about how do I find domain and range of radicals if I didn't have a graphing tool accessible, right? If I couldn't graph this, if I didn't have grid paper or I didn't have a graphing calculator, how could I do this? It's actually pretty simple, so long as you understand what the radical is and what its sort of conditions are. So right here, if you see what I've highlighted, is a little bit of vocabulary. I would definitely put this down in your notes because I will use this vocabulary now and then. This is a radical symbol. I know this because any root symbol that looks like that, that is indicating a radical. The index of that radical is n. And n could be any integer, really. Although I might say, let's stick with positive integers, so whole numbers. So I might have the square root of a. I could have the cube root of a. I could have the fourth root of a. And I think you understand, and so forth. Keep in mind, if n equals 2, then that is square root of a. Yeah, that's square root. So it's actually, whenever you see the square root, it is implied that there's a 2 there. Just so you know. I mean, I don't know. If you ever see this, that is a square root, okay? The letter A is called the radicand. It just means the argument that's inside the radical. It's the thing under the radical symbol. And when we're looking at domain and range, the radicand is what helps us figure that out. So, regarding that index n, if n is even, and I've highlighted this in yellow because it's so important, then the radicand cannot be negative. That is because this will give us an imaginary number. So you see, if I said square root of -2, well, the radicand is negative, that's imaginary. But this also follows for fourth root of -3 or sixth root of -100. As long as that index is even, I can't really put negative numbers there. If I do, the result is imaginary. And so I can't graph those, okay? Now, if n is odd, this is acceptable. I can use any real number, positive, 0, or negative, no real restrictions on that. Think about how the cubic function and the cube root function both have a domain and range of all real numbers. This is kind of true for any radical with an index that is odd. All right, so any fifth root, like so, that's fine. I can put negatives in there and it's okay. For example, if I said the cube root of -125, that is equal to -5 because negative times negative times negative yields negative. And that's what this reason here says, right? I can't have even roots of negative numbers to be real numbers because whenever you multiply a negative number an even amount of times, if that's 4 times, that result is never going to be negative, right? It's never going to be negative. It's always going to be positive. With odd roots, though, if I multiply like 3 negatives, that equals a negative. Or if I do 5 negatives, that's equal to a negative, right? And so that's why that's allowed. So the main idea is, if you're looking for the domain of a radical that has an index that is even, just set the radicand, the thing under the symbol, greater than or equal to 0. Solve that value for x, that's your domain. And if you have n is odd as an index, then the domain's going to be all real numbers, and you don't really have to do anything. So I only have 3 examples here. They're very short, and here's how we do them. So, like I said in red, the main idea, if n is even, set the radicand greater than or equal to 0. So I will look, this piece, x over 5 plus 3, that's the radicand, right? So the radicand is x over 5 plus 3. And the way to find the domain is I want this value, whatever x over 5 plus 3 is it needs to be positive or 0, so it needs to have this restriction. It must be greater than or equal to 0. This is a Algebra 1 inequality to solve. So I will just subtract 3 from both sides. Say here is x over 5 is greater than or equal to -3. Of course, multiply both sides by 5, and I get x is greater than or equal to -15. Hurrah! And so that's it. That's your domain. So if I wanted to do this in interval notation, if x is more than -15, I would say it starts at -15 and continues up to infinity. Oops. And that is that. Done. Now if I'm looking at, I'll do a little star like that. I'll switch colors so that it's very clear. Here's number 2. In number 2, g of x equals -3 times cube root, blah, blah, blah. Well, what does it say in red up there? If n is odd, in which case this index is odd because it's 3, it's a cube root, then I know the domain is going to be all real numbers. So that's all I got to do. The domain is all real numbers. Or I could say, oops, I'm in the habit of writing that. Or I could say the domain is, let's say domain is all real numbers or -infinity to positive infinity. Remember, we can use either one of those, right? That's a terrible shape. I'm going to redraw that box just real quick. All right. Let's go on and do one more. We'll do this one in green. That is h of x equals the 6th root of 7 minus 2x. Again, the index is even, right? Index equals 6 is even. So just set the radicand greater than or equal to 0. So I'm going to say, boop, radicand is 7 minus 2x, and that is greater than or equal to 0, and I will just solve that for x. So I could pretty easily do that by adding 2x to both sides. I'm not even going to write that. 7 is greater than or equal to 2x, and of course divide by 2, so I get x is less than or equal to 7/2. Yeah? This says 7/2 is greater than or equal to x, so flip it, right? If you wanted to flip it, x is less than or equal to 7/2. So my domain is from -infinity up to 7/2 inclusive, so I use a bracket because it's equal, right? And you say, why did I start at -infinity? Well, it's less than 7/2. So it has to be from 7/2 going to infinity. So we start at -infinity and go up to 7/2. And that's it. So that's it for part 2. Nothing else really more to say. It's a pretty basic idea of just setting the radicand greater than or equal to 0 to figure out the domain. This can be really useful when finding the endpoint for a even index function. So if you ever want to know where the endpoint is, meaning this guy, right? If I want to find that endpoint, just set the radicand equal to 0. Because if you go into the negatives, that's when the function doesn't exist in the real plane anymore. And so, yeah, it's kind of like that boundary point. So I do have a set of practice problems for you to try. I would try all of these. I think the challenge problem is kind of fun. At this point, you could just pause the video or go visit the notes online to see this. I'm not going to work out these problems. These are more or less homework problems for you to try. I highly encourage you try them. At least the first 2, okay? I mean, even if you just get the first one. Give these a go. Make sure you're good, because we're going to be doing problems just like these in class. So this is a good opportunity to figure out if you have any questions. That way you can ask me when we get to class. Okay? All right, that wraps up this video. Hope it was enjoyable.